Welcome to everyone who's joining us for our first keynote talk of SciMLCon. We're glad you can all be here. It's my privilege to introduce Andreas Rößler. I hope I've pronounced your name right, who is a professor of mathematics at Universität zu Lübeck, where he has been since 2011. Professor Rößler is a foundational figure in the field of numerical methods for stochastic differential equations, and he's made significant contributions to the development and analysis of Runge-Kutta methods for SDEs and more general numerical methods for SPDEs. And recently he has some very interesting work on forgery detection, apparently, in images of human faces. So I think today he's going to tell us a bit about stochastic Runge-Kutta methods that allow for higher order approximation methods, and maybe a bit about an associated Julia library they've been developing for some of the tooling that play a role in those approximations. So Professor Rößler, thank you for being here, and please take it away.
Yeah, thank you for the nice introduction, and thank you for the invitation to give this talk here. So it's a great pleasure for me, and I think I will talk about simulation of stochastic dynamical systems today. And for this, we will focus on Runge-Kutta methods. So these methods are especially designed for stochastic differential equations as well as stochastic partial differential equations. So the outline of my talk is as follows. So we start with a motivating example. So the question is, why should we consider random dynamical systems instead of deterministic dynamical systems? And after that, we will dive into the numerical point of view for stochastic differential equations. So I will present you some numerical methods and describe how they work and what are the advantages of these methods in order to solve stochastic differential equations. And then we will see that one thing is very essential to get very good approximations, and that are Levy areas. So we will spend some time on the simulation of these Levy areas. And finally, I will, in the second part of my talk, give you a small outlook to the application of such methods to stochastic evolution equations, or more specific on stochastic partial differential equations. So that's the outline, and so let's start with the introducing question. So the question is, why should we consider random dynamical systems? So I think most people know the very famous model of predator-prey, which is from biology, and so we can describe the size of a population. We have the population of the prey denoted by x1, and we have the predators. The population is denoted by x2, and this can be described by some Lotka-Volterra ODEs as they are given here, for example. And if you simulate such a model, you can see a behavior as it is presented in this picture here. So this looks very, very deterministic, very we are repeating. So we have something that is a little bit boring, a biologist would say maybe. So this is, if you compare this with real data, this will not be the case that you see such a periodic behavior, let's say. And now the question is, what can we do to get more realistic models? And one way to come to more realistic models is we can consider the parameters that enter into the equations. And there we have two parameters, that is the birth rate and the death rate for each of the two populations. And if we would introduce some uncertainty on these parameters, which change from time to time, then we can add some noise term to this model, which captures the uncertainty that's in these parameters. So if we add some noise to these two equations, and if we simulate now these two equations, then we get a realization which can look like this in the second picture here. And this looks much more realistic to real data. And so it makes sense to consider some uncertainty that we don't know exactly. So we model this by some distribution, and so the noise comes into the play. But you have to be careful now, because this is just one realization of the equation that we have if we enter some noise, and another realization can look totally different. And why should we simulate such realizations now? Now we are interested in questions on probabilities. What is the probability, for example, that the population size is larger than a certain value or gets below some limit or something like this? So if we simulate a lot of these realizations, different realizations, then we can get some information about the probability distribution, about the probability that something special happens. And here we can see another realization on the left figure. And then something very interesting can happen in a stochastic model that cannot happen in a deterministic model. So what we can observe in the last figure on the right-hand side is that the population dies out. So this is a situation that can happen in a stochastic model. And we are interested in the probability that such an event occurs. What is the probability that the population dies out, for example? And this can be calculated with a stochastic model where we incorporate the uncertainty and the parameters. But this cannot be done with a deterministic model. So I think this is a good reason to start to consider models where we have uncertainty incorporated by some noise. And the question is now, how does the noise look like such that we can get a reasonable model? So we start with a arbitrary ordinary differential equation, which is a model for many things. And now we can think about how to add some noise to this differential equation. And if the noise term, or if, for example, the parameters in the last model are randomized or uncertain, and if we assume that this uncertainty changes from time to time, then we have to add a random process. So something that depends on the time as well. And the most common process, or most widely used process, is a Brownian motion, or called also Wiener process. And this is a very nice process because this occurs very natural if you start with a discrete time model and go to the limit for a continuous time model. And then you, by a central limit theorem argument, you naturally end up with a normal or Gaussian distribution, which is a key feature of the Brownian motion. So for those who are not familiar with the Brownian motion, just a definition here. So these are four characteristics which describe a Brownian motion. And the most important one is that we have a continuous, in time, continuous process. And the increments of the Brownian motion are normally distributed and independent whenever the time intervals do not overlap. So we have stationary increments that are independent. Here we can see a simulation of a realization of a Brownian motion. On the left-hand side, a one-dimensional Brownian motion. And on the right-hand side, we can see a three-dimensional Brownian motion. So this is a typical thing that you can use to model, for example, if you have some smoke, and if you consider one particle in the smoke, and now you can observe how it evolves in the space or in your room after a certain time. So this is a kind of diffusion that happens there. Okay, and if you use a Brownian motion or Wiener process in order to model the noise term, then you come to stochastic differential equations. So there are many applications. In principle, you can use any ODE model and add some noise to get a stochastic model. And most, or some very popular models are the Lotka-Volterra equations that we have just seen. Then we have the SIR model, which is for epidemic diseases like COVID-19. It is used in computational neuroscience for circuit simulation, and there's a big field in mathematical finance where you want to calculate some option prices. And there are many more applications, of course. So now have a closer look to the theory behind stochastic differential equations. So what we have, or what we start with, is a probability space. We have a filtration which fulfill the usual conditions, and we consider a m-dimensional Wiener process, or also Brownian motion called. And then we need some drift and diffusion functions. So A is a drift function, which gives us the mean direction in locally, so to say. And then we have this diffusion function Bj. So these diffusions control the intensivity of the noise component. And then we can consider a stochastic differential equation as it is given here. So this is written down as a differential form, but if you want to give sense to it in a mathematical sense, then you should consider integral equations. So this can be written as an integral equation, but usually this is a shorthand notation that we use for differential equations. So we have the drift part, which comes from the ODE, let's say, and then we have these diffusion terms, Bj, which are driven by independent Brownian motions, Wj. And of course, we have an initial condition. This can also be a random variable, but can also be deterministic. So here in this talk, we, for simplicity, stick on some standard assumptions. So we assume that drift and diffusion functions are globally Lipschitz and satisfy linear growth conditions. So this assures that we have the existence and uniqueness of some solutions. Okay, these assumptions can be weakened, but for simplicity, we take these assumptions now here. So what we are interested in is the approximation of single trajectories. So we want to fix some small omega, and then we want to approximate one realization of our stochastic differential equation. This is different to the point of view when we talk about weak approximation, where we want to approximate some distributional characteristics, for example, the expectation or the variance, something like this. So if we have a look at the picture here, we can see 10 different realizations of a solution of a stochastic differential equations. And of course, we could also consider this red curve here, which is the mean, the expectation of the solution evolving over time. So this is much smoother, of course, and you can approximate this with weak approximations much easier than approximating single trajectories, which are very rough paths, which comes from the Brownian motion, which is a rough stochastic process. So the Brownian motion is nowhere differentiable, and it's Hölder continuous with an exponent less than 1/2, so it's a rather rough path. So this is why we get only low, or we can expect only low orders of convergence if we want to approximate these trajectories. So the first thing is that we have to discretize the time, which is done by these step size or these time points t0 up to tn, and we have a step size hn, and we have a grid on the time interval, which is denoted by ah, and the approximation process will be denoted by y in the following, and depends, of course, on the step size h. And h will always be the maximum step size that we consider on this time interval from t0 to capital T. So now what is the error criterion that we want to consider? So we consider the pathwise or strong approximation, and that is we consider the root mean square error of our solution x at time point t and approximation y at time t. And so this is a L2 convergence, and if the error can be bounded by some constant c times the step size h to the p, then we say our approximation process or approximation method converges with order p. So the most well-known and widely used approximation scheme is still the Euler-Maruyama scheme, which is given here. So this is because it's easy to implement, easy to understand, and it's very, I think, widely used. But in this talk, I want to show you that this can be done much better than with the Euler scheme. So the Euler scheme is simply considering the stochastic differential equation, and then we fix the integrands, the drift function A and the diffusion functions B, and hold them constant on each time interval. So this is the idea behind. And then we have these delta W, which are increments of the Brownian motion. So these are simply normally distributed random variables that can be easily simulated. So this is a very simple scheme, and the order of convergence for this scheme would be 1/2 with respect to the root mean square. Now the question is, how can we do these things better? And so we want to consider some higher order approximation methods that are efficient in some sense. And therefore, I want to present you the class of stochastic Runge-Kutta methods, SRK methods. And these methods allow for approximations with some higher order of convergence. So the methods are given, the method is given here. So we have the scheme itself, which is a recursive formula, and we go over the time steps. And what is important is we have some stages. We have the stages H0, which enter into the drift function A. And then we have the stages Hk for each diffusion function Vk. Now, further, we have to simulate these random variables Ik and ILK. So these are Ik are increments of the Wiener process, which are normally distributed, so they can be easily simulated. But the random variables ILK are iterated stochastic integrals, and these are hard to approximate. So I will come back to this point later on in the talk. So such a stochastic Runge-Kutta method is somehow defined by its coefficients. And the coefficients in the scheme are the weights alpha I, and the coefficients which are in the stage values, which are A0 and A1. So these are the blue coefficients which correspond to the drift function A somehow, scaled by the step size H. And then we have further coefficients, beta 1, beta 2, and B0, B1, which correspond to the diffusion function and to the stochastic part of the method. So these coefficients can be summarized. We can write the weights alpha, beta 1, beta 2 in some vectors, and we can write the coefficients A and B in some matrices. And then we can put them together in a so-called Butcher tableau, as it is given here. So we can summarize all coefficients in such a tableau. And then, yeah, we have to think about choosing nice coefficients such that we can have a high order of convergence. Yeah, and we can calculate order conditions for such a scheme, which are given here. I don't want to go too much in detail, just telling you that you can solve these equations to calculate some coefficients for the scheme. And then you can guarantee that you have an order 1, a strong order 1 approximation scheme. And the proof can be done by Collat-Rulizzi theory. So now we put in some coefficients such that we have an order 1 scheme, as it is given here now. And we can see that we need 3 stages now. So we have H1, which is equal to Yn, so I didn't write it down again. And we have these H2, H3 stages for the diffusion function B. And then we can think about the computational effort of such a scheme and compare it with well-known schemes. So the computational complexity is considered as the number of function evaluations that we have to calculate in each step. And if we compare this Runge-Kutta method with some well-known schemes, like the Runge-Kutta method proposed in the famous book by Kluden and Platen, or with the Milstein scheme, which is well-known, which is the Taylor scheme, then we can see that the computational effort for a d-dimensional system of SDEs, if we consider the evaluation of the diffusion function, then we have m squared times d. And for the Milstein scheme, we have d squared times m evaluations. And for our Runge-Kutta method, we were able to break it down to a linear dependency on the parameters m and d. So d is the size of the system. We have a d-dimensional system of SDEs, and m is the number of Brownian motions, of independent Brownian motions driving the system. So here we get a reduction, and this is very significant if you consider large dimensional systems. So the savings are immense if you have high dimensional systems that you want to simulate. So these Runge-Kutta methods are very efficient due to the design of the stage values. But we have to keep in mind that we, for all of these methods, all over order 1 methods, we have always to simulate the iterated stochastic integrals. And this is another question which is very important for the implementation. So that is now the next question, why are Levy areas are essential for higher order approximation methods. And yeah, such a iterated stochastic integral as it is given here can be split into two parts. So the first part is the first summand on the right-hand side here, which can be easily simulated. We only need the increments of the Wiener process, which are normally distributed random variables. And then we have these terms A, ij, which are the so-called Levy areas. And the problem is now that we don't know the distribution of the Levy area. So we can't simulate it exactly. And so we have to think about an approximation of these Levy areas. And yeah, many people have been thinking about this problem. And starting in 1988 by Milstein and then Klöden-Platen-Wright, they proposed an algorithm which is based on a Fourier series expansion of this term. And however, the drawback is that the computational complexity is if C is the computational cost, so it depends on C to the -1/2. So this is not very interesting to use these methods, because then you can also use a Euler-Maruyama scheme directly, which has the same computational effort for the same error. So this is makes not much sense to use such an approximation method. And then in 2001, it was Wright and Victorson who came up with a new method. And here, for the first time, they improved the computational complexity to C to the -1. And from this point on, it was possible to apply such higher order methods like the Milstein scheme or Runge-Kutta methods, because now they can be better than the Euler-Maruyama scheme. And however, in the starting, this was only possible for two-dimensional Wiener processes. And then Victorson presented an algorithm in 2001, which also works for general high-dimensional Wiener processes. And this has been generalized. There's some other works here, and has been generalized in cooperation with Claudine Leonard, where we generalized this for the SPDE setting, for the infinite dimensional setting. And very recently, together with Jan Hongrovius, we were able to improve this algorithm by Victorson. It's the same order of convergence, but a better constant, so we can save a computational effort. And that's what I want to talk about next. And therefore, we start with the idea behind this. So as I said before, we consider a Fourier series expansion of a so-called Brownian bridge. And if we consider this Fourier series expansion, we get a representation of the Levy area as it is given here. And the Fourier coefficients are the A and the B random variables, which are simply normally distributed independent and can be easily simulated. So we can put this into a matrix form, which is A of H, and vectorize everything. Then we get the expression given here. And now the idea is to truncate this series for an approximation. So we can truncate this after P summands, and then we have some remainder terms, R1, R2. And the idea is now to approximate also these remainder terms in a suitable way. So the first term, AP, can be simulated directly. This is a finite sum, and the remainder terms have to be approximated in order to get a better approximation order. So the algorithm that we propose works as follows. First, we approximate or we simulate this truncated Fourier series, where we only need normally distributed independent random variables. So this is easy to implement. And then we approximate the first remainder term, R1, by this expression here. So here enters also a normally distributed random variable. And this is not really an approximation. It is exact. Yeah? We know the distribution of the remainder term R1, and we can do this exact here with the exact distribution. And then the second remainder term, R2, is approximated because this is only conditionally Gaussian distributed. And making this, so the idea is the same as by Victorson, who proposed this idea first in his seminal paper 2001. And we just modified this idea a little bit to improve the algorithm. And here we use also a standard Gaussian random variable, which we have to simulate, can be easily done. And then we have to approximate this remainder term R2 by this expression here. So all we need is just to simulate Gaussian random variables. That's easy to do. And at the end, we put everything together to get the iterated stochastic integral values that we need for the approximation method. And they're somehow anti-symmetric in a certain way. So for I less than j, we have the first expression, and the other ones we get by switching the sign somehow. So that's the algorithm, which can be easily implemented. And yeah, if you compare this with the algorithm by Victorson, we get an improvement by a factor square root 5. So this is a factor which it's a factor where we need less computational effort by a factor square root 5. And in addition, we have to calculate a certain covariance matrix, which is very easy. In our algorithm, it's just a diagonal matrix. It's an identity matrix, whereas by Victorson, we need to calculate the square root of such a general covariance matrix, which is also costly computationally. And this new algorithm has been implemented by Felix Kastner, who did a very nice job there. And there's now a Julia package available, which is called Levy area. And so we can use this very fast algorithm very easily now for any higher order approximation method for SDEs. And yeah, if you consider the computation cost of this algorithm and put this together with an order 1 approximation method, then you can consider the error versus the computational effort, which is what we are interested in. And this gives us the so-called effective order of convergence. And this is not anymore 1, as it was for the scheme itself. So order 1 with respect to step size. But if we consider error versus computational effort, then due to the simulation of the iterated stochastic integrals, which is very costly, the order drops down to 2/3 for any order 1 method. But this is still more than 1/2 that we can expect for the Euler-Maruyama scheme. So it makes sense to use these higher order methods. That's the crucial point of my talk. You should apply order 1 methods, but you have to keep in mind that you have to spend a lot of work in the simulation of the iterated integrals. But anyway, at the end, you get an order 2/3, which is more than 1/2 for the Euler-Maruyama method. Considering some numerical examples, just I want to go fast through it. So this is a system of some SDEs, two-dimensional system and a 4-dimensional Brownian motion driving this SDE, and it's a non-commutative case. And what we can see here for the simulation results is on the left-hand side, we consider error versus step size. So we can perfectly see order 1/2 for the Euler method and order 1 for the Milstein method and the Runge-Kutta methods. But this is not what we should look for. We should look on the right-hand side, where we have the error versus the computational effort. And this is what we are interested in, because we want to consider error versus computation time. And there we can see the improvements of the stochastic Runge-Kutta methods compared to the Milstein scheme and to the Runge-Kutta method that has been proposed in recent literature by Glöden and Platen. So we get a reduction of the computation effort by a factor. So this is the shift of the curve to the left-hand side. And the blue line here is the result of the Runge-Kutta method, and the red line here is what we get by the Runge-Kutta method by Glöden and Platen. And if we increase the dimension of the system, so if we consider another example, which is a linear stochastic differential equation here, so we can increase easily the dimension, and we have an explicit representation of the solution, which is given here. So we compared with the exact solution. We don't need a numerical simulated solution as a reference solution. Then we get improvement on the right-hand side, error versus computational effort. And here we can see how the improvement increases as the dimension grows. Now for dimension 10, we can see a very better results of the Runge-Kutta method compared to the Milstein scheme and compared to the Runge-Kutta method by Glöden and Platen. So the blue line is the best scheme here in this example with the smallest computational effort. So what have we seen in this talk? We have seen that stochastic differential equations are important for many models. We have seen that there exist efficient approximation methods of higher order 1 stochastic Runge-Kutta methods, and that we need a very efficient simulation method for the Levy area, which is very important. And what I've not talked about in this talk is about stability issues, about stochastic differential archetypic equations, where I've been working on. I've not been talking about weak approximation or some geometrical numerical integrators. And there are many more results, just to mention a few of them. Multi-level Monte Carlo is very important for weak approximation. There's a lot of research going on non-standard assumptions, irregular drift function, and so on. There has been done a lot of work for step size control in connection with stiff equations, and there have also been some people working on differential equations with not only Brownian motion, but fractional Brownian motion, jump process, Levy process, and whatever kind of noise process. Okay, there's a lot of things going on, and now I'm coming to the second part of my talk, and this is the stochastic evolution equation part, and I just want to give you an idea, not going too much into details now. So what we considered here is a similar stochastic partial differential equation, as it is given here in the middle. And there we have an operator A, which acts on X. And here we assume A is a generator of an analytic semigroup. And we have nonlinearity F, and we have a diffusion operator B. And the whole solution of the SPDE lives in a Hilbert space H, and now we have not a Wiener process, but a Q-Wiener process, which is also a Hilbert space valued process, which lives in the Hilbert space U. And we are considering mild solutions as they're given here. We have the semigroup e to the h times t, which gives us the solution in this form as it is given here. And okay, I'm not going too much into details, just to give you an idea how it works for the infinite dimensional setting. Now we need a lot of assumptions, technical assumption. I'm not going into detail here on the operators and so on. What is important is that our operator A has some eigenfunctions which are orthonormal basis of our space H, and that we can represent the operator A in this spectral form as it is given here. We assume for the nonlinearity F that is twice continuously differentiable, and both derivatives are bounded somehow. And for the diffusion function B, we assume essentially that it's also twice continuously differentiable, bounded derivatives. And we have a linear growth condition. We have a kind of Lipschitz condition for B prime B, and we have this artificial condition, which is given here in the last inequality. And there are a lot of parameters, but don't care about them. That's not so important for this talk now here. For the initial condition, we assume that there exists a force moment, which is finite somehow. Now, there's also been a lot of research going on at the moment on this SPDE stuff. And just to mention one work here, this is the work by Arnulf Jensen and Michael Röckner, 2015. They came up with a Milstein scheme for SPDEs. And this was the starting point for our research when we tried to design a derivative-free method of the same order of convergence, but with improved there's an improved design so that finally we can also increase the order of convergence compared to the original Milstein scheme. And that's what I want to show you very shortly now. So there are two things to do now. We have to discretize the space. So we have to project the Hilbert spaces, which are infinite dimensional, to some finite dimensional subspaces. So this is the spatial discretization somehow, which we do by a projection operator Pn. So we consider here a spectral Galerkin approximation. And then we consider discretization of the time, which is done by equidistant discretization with step size h. And then we can expand the Q-Wiener process in a series, as this is given here, where we have some scalar Brownian motions, beta, or increments of these Brownian motions, delta beta, which enter to the series. We have these eta j, which are the eigenvalues of the covariance operator Q for the Q-Wiener process. And here we have the eigenfunctions of the Q-Wiener process, which are orthonormal basis of the space U. Although this can be very easily be simulated. And now for simplicity, we assume a commutativity condition. So we assume that P prime B is somehow symmetric in the two arguments u tilde, so you can switch them and it is the same somehow. And this allows us to only to need increments of the Q-Wiener process. And then the derivative-free Milstein scheme can be written down in this form here. So the first part, the first line, is essentially an exponential Euler scheme. And then the rest of this scheme is an approximation of B prime B somehow. And the most important thing here is, you don't have to go into details here, but the most important thing is that we did this in a very sophisticated way, such that we can reduce the computational effort. I'm running a little bit out of time. Huh?
Just giving you a 5-minute warning till the next talk. So
yeah, okay.
Feel free, don't rush, but just wanted to let you know.
Thank you. So we can prove convergence results, and I want to jump to the simulations. So we consider a Laplacian operator here, and then we get a reaction diffusion equation as it is given here, and then we can apply this method. And this is very similar to the SDE setting, but now we get an improvement of the order of convergence, not just a reduction by factor of the computational, but an improvement of the order of convergence. So the blue line is the proposed Runge-Kutta method, and we get the highest order of convergence compared to the original Milstein scheme, which is here in magenta color. And then we have the result for the exponential Euler method and linear implicit Euler method, green and red line, which are really the same. And we can see we get an improvement of the order of convergence. So this is very interesting. We have a derivative-free method and higher order of convergence. And another example with a nonlinear diffusion that we used, the same effect. And here we can see the Milstein method has the same order as the Euler method, but our Runge-Kutta method can improve the order of convergence. So what you can take home is that higher order methods are very efficient, but in the general case, you have to simulate iterative Stochastic integrals. Expect of the situation we have commutative noise, then you can work with increments of the Wiener process only. So thank you very much.
All right. Well, thank you for a really nice talk. We do have several questions posted on Discord, and there were a bunch of questions about multi-level Monte Carlo. And so I think
you might want to turn off close the YouTube tab. I think there's an echo coming in.
There's an echo coming in.
Yeah, on your audio feed.
Is there still an echo?
Now it's fine. Oh,
that's weird. That was a completely different computer that shouldn't have even had the microphone on. Okay. Anyways, my apologies to everyone. So I think Chris kind of summarized maybe a bit of the issue, which is, could you comment kind of on the trade-off between, say, variance reduction using multi-level Monte Carlo versus, increasing accuracy versus higher order methods? Is there a lot known about the kind of trade-off between the two and which is going to dominate?
Yeah. So the multi-level Monte Carlo method is for more or less for the weak approximation situation, where we want to approximate expectation of something functionals applied to the solution. And these methods are really designed for the strong approximation, L2 error. So this is a different error criterion. You can use them for multi-level, but this is not efficient. I would not recommend this. So you should rather use very specialized methods for multi-level. And I think there exists a Milstein method, which is based only on increments of the Brownian motion, which is very fine. And we are working on a Runge-Kutta method for this version. And otherwise, you can combine strong approximation methods, Euler method with strong approximation properties, together with a weak approximation method on the finest level of the multi-level Monte Carlo. And then you get also very nice results. But these methods I presented today are not recommended for weak approximation. Today I only spoke about strong and L2 approximation.
Oh, great. I actually had a question too. So I guess one thing I wonder about is I do like a lot of simulations of reaction diffusion systems. And so I wonder about, with these kinds of methods, have you investigated, or are there adaptations of them to try to be positivity preserving for solutions, or to try to recover stationary distributions? Because I assume the convergence results are finite time in general.
Yeah, you're right. These are very interesting questions, especially for the SPDE setting. And I have to say, we are only at the beginning, or for myself, I have to say, we started to prove conversions for these results, for these methods. And we are now working on methods where we don't need this commutativity condition. And this works also very fine together with the iterated stochastic integrals. But now the next step is to consider stability issues or positivity to serving or whatever you can think about. But the first step was for us to have a method that converges. And now we can think about how to modify these methods such that they have nice properties, as you mentioned. But this is not, we are not coming along this. So this is maybe on the plan for the future projects.
Sure.
But yeah, that's very important.
Okay, great. Well, I think we need to move on to keep on schedule, but thank you again for the talk, and I will give you a blessing.
Thank you very much.